Okay, so another short lesson today to go with 4.5, a new definition for something that we've already talked about, and then a little review of the invertible matrix theorem. So in 4.6, we're going to talk about rank. And before we talk about what that means, though, we're going to review a little bit about column space and rows, and now something called row space, and also the null space. So we are now going to look at the set of all linear combination of the rows of the matrix A. That's going to be called the row space. Just like the column space of A was all linear combinations of the columns, all the possible linear combinations of the rows is going to be denoted by row A. And they're going to be essentially, they're the same concept, but they're not going to be the same dimension necessarily. They're also not going to be the same, now that I think about it, I think they are going to have the same number of elements though, because each of these, the row space and the column space, are going to have to do with the number of pivots. So let's take a look at an example, and I'm covering this up with yellow sheets of paper because I was too lazy to go print my own notes. So I'm just going to write it on this yellow paper here. So for example, here we have this matrix, and we have 3 different rows. Notice that I used to be able to think about the columns as vectors. I can also think about the rows as vectors separately. So, okay, the row space of A is the span of these 3 rows. What are all the possible linear combinations of these 3 rows listed either here in the matrix or here out to the side? Now I've noted here that this is a subspace of R4. If you need to remember why a span is a subspace, go back and review I think 4.1 and 4.2. But it's a subspace of R4 because each row, each vector here now looking across, has 4 entries. Okay, so again, the column space for A would have been some subspace of R3 because they have 3 entries, but this is a subspace of R4. Okay. Okay, so again, we can write row vectors horizontally, but they could be written as columns if it's more convenient, and we can do that by making the rows into columns by using a transpose. Okay, so just transposing the matrix, so the transpose of this matrix here would be a 4 by 3 matrix. Okay, remember this is currently a 3 by 4 matrix, so the transpose would be a 4 by 3 matrix. And then that would make our rows we've listed here into new columns. I don't know why there's a 0 here. I should close that. Okay, all right. Again, row space of A is the column space of A transpose. Now, the important thing is how does this relate to row operations? Okay, we've got a couple of statements here. When we use row operations to reduce the matrix A into a new matrix B, okay, what we're doing is we're taking linear combinations of the rows of A and coming up with B. Okay, think about it. 2 of row 1 plus row 2. Okay, that's a linear combination. We're just making multiple linear combinations. So we could reverse this process, and that's what's key. We could reverse this process and use row operations on B to get back to A. Okay, this is where the row space becomes unlike the column space. The row space of A will be equal to the row space of B. So if 2 matrices are row equivalent, then their row spaces are the same. To write the row space, you could either use the original rows or the row reduced rows. This is unlike the column space. Okay, the column space you have to look at which ones are linearly independent and then choose, when you're writing a description of the column space, it's a span of the original vectors. Okay, all right. So here's what I said. If 2 matrices A and B are row equivalent, their row spaces are the same. If B is an echelon form, the non-zero rows of B, notice it has to be non-zero rows to form a basis, and that's because a basis has to be linearly independent. So if we had a row of zeros, that would be a dependent vector. Okay, so the non-zero rows of B form a basis for the row space of A as well as B. So here, let's take a look at an example. Okay, so I've got this matrix, which is the same as the one I gave you earlier, and B. These 2 are row equivalent, and this is not in row reduced echelon form, but it is in echelon form. Not row reduced, but just echelon form. Okay, right, and that's what I wrote here. A when reduced, made to B. Not row reduced, but just when reduced to echelon, made it to B. Okay? We're trying to find a basis for the row space, the column space, and the null space. Okay? And we're going to look at the dimension. Remember last time we figured out that the dimension is the number of basis vectors in the basis. Okay? So to find the basis for the row space, we can actually use two non-zero rows of B, or we'd use those rows of A. So since this last row got completely eliminated into a row of zeros when we reduced from A to B, I am going to say that the row space of A, which is equal to the row space of B, will be the set of, and I'm going to write them as rows. Okay, so the set of vectors that are, I'll write them in parentheses, -1, 2, 3, 6, and 0, -1, 0, 0. Oops, I didn't make sure I put my commas in there. Or the set of vectors that are -1, 2, 3, 6. Oh, my notation is bad. Here we go. And the second row, 2, -5, -6, -12. Now, here is the problem. Okay? I know that will work because I know that there has been no row switching between these two matrices. If there has been row switching, then how do I know that it was row 2 that was linearly independent from row 1 and row 3 was the dependent one? Okay, so that's why I think it would be best if you stick with the vectors you result at the end, because you're not sure if in your row reduction, especially if you do it in your calculator, if there was a row switch, then we're not entirely sure which one of these rows was linearly independent from the other ones. Okay, just make sure you're also choosing non-zero rows though. And that's also not a problem if you're row reducing by hand, but I know you guys are a little bit lazy, so you don't want to do that. Okay, other questions. Find a basis for the row space, we did that. A basis for the column space, okay, well I can look here and I can see which ones have free variables and which ones don't. So for the column space of A, oh, and I asked for the column space of both, but here this is true. Okay, the column space of A, which is not equal to, keyword here, not equal to the column space of B. Okay, and think about it. Here, what I'm about to do is write the span of vector 1 and vector 2, because I can see that those are where the pivots are. I'm not going to do it for 3 and 4 because those are the dependent free variables. Okay, the span of the first two vectors can get me a non-zero entry in row 3. But the span of these two vectors cannot get me a non-zero entry in row 3, which is why the column space of B and the column space of A are not equal. But a basis for the column space of A would be the, I should write span, just like I did here. Sorry, span of those vectors. Span of the first two vectors in my matrix, because when I row reduced, I found that those were the basic variables. So -1, 2, 1, and 2, -5, -3. Okay. All right. Oh, I forgot to write my dimension. Okay. Again, here, columns with pivot. Dimension of the row space of A and the dimension of the row space of B was 2 because there are two vectors in the basis, which means that the column space of A, dimension of the column space of A, is also 2 because there are two vectors in the basis. Now what we needed finally, and I'm going to go ahead and just move my paper down for this one because it requires a little bit of calculator, which you should do yourself. If I'm trying to find a basis for the null space of A, in order to do that, I need to find the solutions to AX equals 0. So remember, the null space of A is a set of vectors that is all solutions to AX equals 0, meaning we actually have to solve that equation first. So what I did here was I row reduced, okay, and this is what I got. We only had to do one more step. And then we had to multiply by some negative ones, but that's okay. So I wrote it out as an equation, but then I wrote it with my free variables in parametric vector form, which meant my null space is the span of this vector here and this vector here. Okay, the coefficients of my free variables. So that is the basis for my null space, and the dimension is 2. Okay, all right, so that's a little bit of review for row space. And hopefully, please ask in office hours or just send me a text or something like that if you have a confusion about the difference between the row space and the column space and why we can use the original rows or the ending rows, but we can't do that for column space. All right, so let's take a look at the next page. Okay, so a couple more facts here that are nice. Okay, the dimension of column space of A is the number of pivots. Okay, it's also the number of non-zero rows in B, the row-reduced matrix. It's the dimension of row A. Okay, so the dimension of the column space of A and the dimension of the row space of A are both just how many pivots does A have when I've row reduced. The dimension of the null space will be the number of free variables. Okay, all right, so we have a new word, and that word is rank, and it describes the dimension of the column space of A. So basically the rank is the number of pivots a matrix has. You can think about it that way. I'll add that in. Number of pivots. Okay. All right. And we can make this a nice little equation though, and we talked about it in the last video. The rank, which is the number of pivot columns, plus the dimension of the null space, which is the number of free variables or free variable columns, will equal the total number of columns. Okay, so rank plus dimension of null space equals number of columns. Okay, and notice that I had to put dimension of the null space because adding a number to the null space, that's just like doesn't make sense. So a couple of questions kind of to test our knowledge. Okay, again, dimensions of the column space and the row space are equal. This common dimension, which is called the rank, also equals the number of pivot positions and satisfies the equation rank A plus dimension of null space equals the number of columns. Okay, also, since the row space of A equals the column space of A transpose, the rank of A equals the rank of A transpose. Okay, and now we're just going to test some questions. All right, so suppose that I have a 5 by 8 matrix and I know that it has a rank of 5. I want to find the dimension of the null space, the dimension of the row space, and the rank of A transpose. And then finally, after I've done that, answer the question, is the column space of A equal to R5? So first thing, I have a 5 by 8 matrix. Let me scroll up a little bit. Which means I have 5 rows, 1, 2, 3, 4, 5, and 8 columns. 1, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so a matrix of this size. It has rank 5. That means it has 5 pivots. So I'm going to go ahead and just put them along the diagonal because regardless, I will still have the same number of free variables. So I have a pivot, 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 pivot. Okay. So that means there are 3 free variables, which means the dimension of the null space of A is 3. Okay. Nice, because that's the number of free variables. And the dimension of the row space of A will be the same as the number of pivots, which is 5. Okay, the rank of A transpose is up here. Row space of A is column space of A transpose. Rank of A equals rank A transpose. Okay, which is the same as dimension of row space, is also 5. Okay, last question. Is the column space of this matrix equal to R5? That's the same question as asking ourselves, do the columns of A, this matrix, span R5? And since I have a pivot in every row, and there are 5 rows, yes, there's a pivot in every row. Okay? So we can kind of use this basic information to tell us a lot about the size of different things. So let's try, and here I've done an example here. Okay, let's try another one. Grab a different sheet of paper. For a 9 by 12 matrix, what is the smallest possible value of the dimension of the null space of A? So that's the same as asking, what are the least number of free variables that I could have? So for a 9 by 12 matrix, that would give me 9 rows and 12 columns. the least number of free variables I could have would be, so the dimension of the null space of A, let's write an inequality for this, will be greater than or equal to 3. That's the least number that I could have because I can have a pivot in every row, but I can't have a pivot in every column. Okay. All right, and then one more before we review our, I need to give myself more space. Sorry, I'm gonna move the plants. All right, here we go. A scientist solves a homogeneous, homogeneous, that means it's AX equals 0, sorry, 50 equations in 54 variables and finds that exactly 4 of the unknowns are free variables. Okay, so that means we've got 50 equations, that's the number of rows, in 54 variables, that's the number of columns, and I can see that exactly 4 of them are free. So 4 free variables. Okay, can the scientist be certain that any associated non-homogeneous system with the same coefficients has a solution? So basically we're asking ourselves, there are 4 free variables in the solution to AX equals 0. If I use the same coefficients, regardless of what I put over in the side, will I be able to get a solution? Well, if there are 4 free variables, that means that there have to be 50 pivot columns. And if there are 50 pivot columns, that means there's a pivot in every row. So 4 free variables implies 50 pivots, which implies a pivot in every row, guarantees a solution to AX equals B for all B in 50th dimension, because it needs to match the number of rows. Okay, all right. So let's take this and let's add on to our invertible matrix theorem, and then we'll be done. Okay, just test a couple of examples. Get some new paper right here too. All right. Do you like my smiley face? All right. So first, we are starting with A be a square n by n matrix. On the chapter 2 and 3 test, there was a question that asked, how do you know that the matrix is invertible after you multiplied XA equals I? The key was here that X times A equaled I, and established in the problem was X and A are square. Okay? In order for that to be true, that tells us that both matrices are invertible no matter what. If an inverse may exist, but it would only be on one side or the other side. But the key here for our invertible matrix theorem is that we do have square matrices. Okay? All right. So, a couple more things to add. We're getting down to M through R. I think I did tell you that this theorem is enormous. But more theorems to be added on. The columns of A form a basis for Rn. Notice that this is a square n by n matrix. And again, these are all equivalent to the fact that A is invertible, pivot in every column, pivot in every row, that kind of thing. All right, so the columns of A form a basis for Rn. That makes sense because in order for it to be a square matrix and for the invertible matrix theorem to apply, we need to have a pivot in every column, okay, which means they are linearly independent, and the span of those columns will be Rn because that will be their size. Okay, so the column space of A span Rn means the column space is Rn. The dimension of the column space is n. The rank of A is n. And the dimension here, because the rank plus the dimension of the null space is supposed to be equal to n, this makes sense. The dimension of the null space should be 0, indicating that the only solution to AX equals 0 is the 0 vector. The null space is only the 0 vector. So let's test a couple of these theorems. So we've got a 6 by 3 matrix that has rank 3. Okay, so 3 pivots. What is the dimension of the null space, the dimension of the row space, and the rank of A transpose? So if I have a 6 by 3 matrix, okay, well hold on, let's space this out. I have 6 rows and 3 columns. 1, 2, 3, 4, 5, 6. Okay, has rank 3, which means there are 3 pivots. Okay, what is the dimension of the null space? Well, if there are 3 pivots, the dimension of the null space, all of these columns are linearly independent, which means the dimension of the null space should be just 0. Okay? The dimension of the row space, though, because we're going to have row-reduced vectors, okay, is going to be 3, because that's the number of pivots. Also because when we row-reduced, all of these would be rows of zeros, which we would not want to include in our row space, or the basis for our row space. The rank of A transpose should be equal to the rank of A, so rank A transpose should also be. In the next example, we have a 5 by 6 matrix, so 5 rows, 6 columns, and it has 4 pivot columns. Okay, first, what is the dimension of the null space? Meaning, how many free variables are there? Okay, so if we have 4 pivot columns and 4 total columns, the dimension of the null space should be 2, because it's going to be the number of free variables. Okay, second is the column space of A in R4. So this one's a little tricky, and I've wrote up a little explanation over here on the side. So my dimension of null space is 2. Okay, there are 5 rows and 4 pivots. So the columns of A can't span R5. That's clear, because there would not be a pivot in every row. Additionally, each column has 5 entries. So all the vectors in these columns are in R5. Because we don't... Nope, sorry, I want to take that back. Sorry, thinking about that. Okay, so even though there are 4 pivots, the column space of A is not in R4 because each column itself is not in R4. But theoretically, we could use those 4 pivot columns to reach any point in R4 if we reduce the dimension, if we kind of forgot about that last part. But the question was just, is the column space in R4? And the answer is no. The column space is still in R5 because it does have 5 entries. And notice that, remember, for the column space, we are also using the original vectors. So if the original vectors had entries, had their 5th entry, let's say like 1, 2, 3, 4, 5, okay, this entry was a non-zero entry, we couldn't just forget about it and reduce it to be in R4. Okay, so we're saying the column space does not span R4 either, because we're, in this scenario, not 100% sure. They're not even in R4 because there could be a non-zero entry at the bottom. Okay, sorry, that was a little confusing. But example 7. If we've got a null space of a 7 by 6 matrix, the null space is 5-dimensional. That means there are 5 free variables. What is the dimension of the column space? So 5 free variables, but we have 6 total columns. That means the dimension of the column space should be 1. There you have it. Okay, remember adding those together to get number of columns. Okay, another one. If the null space of a 5 by 6 is 4-dimensional, meaning 4 free variables, what is the dimension of the row space? Well, the dimension of the row space is the same as the dimension of the column space, aka number of pivots. So if I know that there are 4 free variables, but 6 total columns, that means there have to be 2 pivots, which means the dimension of the row space and the dimension of the column space is 2. Okay, and last one. If A is 4 by 3, what is the largest possible dimension of the row space? So, okay, the largest possible dimension, meaning the least number of free variables, the most number of pivots. Okay, so that means I have a 4 by 3 matrix. Okay, that means I would have a pivot in every column, which is possible. Okay, but, and I drew this a little wonky, that's not possible to have a pivot in every row. Okay, but because the dimension of the row space of A is the same as the dimension of the column space of A, the largest possible dimension for the row space should be 3. All right, and that is our last example. Okay, so if you have questions, come see me in office hours. Hopefully this goes together well with lesson 4.5, and we got to review and add on to a little bit the invertible matrix theorem and define rank.